Welcome to How to Succeed in ECE Without Really Trying. I'm Dr. Linda DeBrunner, and today I'm going to be talking about active RC filters, and this time it will be a bandpass filter. Here's another op-amp circuit. We still have our op-amp. We still have our negative terminal and our positive terminal. The positive terminal is still connected to ground, okay? The reference point for our circuit. And what we notice now is that we can talk about this as an impedance C1, and this will be our impedance CF. So I want you to remember then that Z1 is going to be the series combination of R1 and 1 over SC1, and ZF will be the parallel combination of 1 over SCF in parallel with 1 over RF. Okay, just like we did with resistors, we can derive this. The rule is going to follow the same format. So ZF, let me just write in general, remember, Z parallel of Z1 with Z2 will be equal to 1 over Z1 plus 1 over Z2. Okay, that's the parallel combination. So we can plug that in for Z. We could have, so ZF in our case will be equal to 1 over SCF. See, that's where you mess up, right? 1 over SCF plus 1 over RF. Okay, I noticed a little mistake here. I should have written RF, not 1 over RF. Okay, so ZF will be equal to 1 over SCF plus 1 over RF. This term, of course, right here is just, this term right here is just SCF. Then we can multiply through by RF over RF, and we end up with this expression for ZF. And then our source impedance on the source side was R1 plus 1 over SC1. We're going to find the common denominator. We get a 1 plus SC1 R1 over SC1. Okay. Now this circuit we have looks just like the other two circuits we've looked at before, except that now we have a series combination here and a parallel combination there. But in each of these cases, this is just a basic inverting amplifier that with a gain of minus ZF over Z1. So when we use that idea, we plug in for ZF and Z1, we end up with this expression. Okay, you could have derived it again, and feel free to do so. Write your equations. If you write your equation here, you can do each of these independently if you want. You will still come up with the same answer. So this just gives you more ways to work the same problem. So feel free to do that to get a little more experience. Okay, so when you plug in ZF and Z1, we end up with this as our gain. If we look at what happens when omega is equal to 0, the gain is going to be 0. And if omega is equal to infinity, it approaches infinity, then we end up with 0 as well. Okay, and how did I know that? Well, I plug in, I throw away the ones because they don't matter, and then I have infinity over infinity squared, so that means that the gain is going to 0. Okay. So sure enough, this is a bandpass filter, and it's important to note that it's some constant times a low-pass filter times a high-pass filter. Okay, so we can take this and put it into MATLAB with some values. Okay, I can define the numerator, define the denominator. For the denominator, I could have multiplied it all out, and then had S squared, S1, and S0, S to the squared, S to the 1, S to the 0 terms, but you can also use the MATLAB function to do that for you. Then you can plot using freq S, and we end up with a bandpass filter. Okay. To figure out if it's a bandpass filter, we don't worry about the phase response, only the magnitude response. So if I blow this up, just to give you a little more experience, it looks like, and we could calculate it, but it looks like the gain is 10, which I think is what it should have been. And the frequency response is in the pass band. The phase will be minus 180 and 180, which is basically a minus sign in both cases. So that's where you get the minus for your gain. Okay, let's look at the pass band again. So if it's 10 in the pass band, right, we read over here 10. So 10 minus 3 gives us 7 dB. That will be our 3 dB down point. I can blow this up. We can see 1, 2, 3, 4, 5, 6, 7 right here, and then 8, 9, 10. Okay, so if I could have counted down. 1, 2, 3, 4, 5, 6, 7 is right there. 8, 9, 10. So there's 7. And this one's a little bit easier than the other because I've got a dotted line drawn in for me. And I can bring it down. Let's see, I'll draw as neatly as I can. Okay, and so when we want to look at the cutoff frequency here, find the 3 dB down point, read it off. Well, here we have 10 to the 0, which is 1. Here we have 10. Here we have 100. Okay, so remember that the magnitude response is log-log. So 10 to the minus 2, 10 to the minus 1's in the middle, 10 to the 0, which is 1, 10 to the 1, 10 to the 2, 10 to the 3, etc. So our corner frequency on the low side will be 10 radians per second. And we can also find the corner frequency on the high frequency side. These graphs are nice because they kind of give you on both sides. Again, we wanted 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so there it is. Right there. And then I come down and read down, and it is 10 to the 8th. So our corner frequencies are 10 radians per second and 10 to the 8th radians per second. That is a very broad pass band. Okay, so there you go. That's a bandpass filter. Now let's see what this really means in practice. Okay, I wrote some MATLAB. You can refer back to it if you want later. But basically what I'm going to do is I'm going to take an input in the pass band. I'm going to simulate with LSIM and then plot the figure. Okay, and then so that's basically calculating the what's happening to the output. Okay, what the output is for that input. And then I'm going to look at two other situations. We're going to look at a frequency below the pass band. And so we can tell that right here. So here we had 100 radians per second. That's in the pass band. Below the pass band, I had 0.1 radians per second. And then the third one, I'm going to look at above the pass band, and I'm going to have omega is equal to 10 to the 10th radians per second. Okay, so when I look at those in turn, this is what I see. So here is the input frequency within the band. Okay, the input shown in blue, and it was let's go back and look. What did I make it? I made it 5. In all these cases, I made the amplitude 5. So there we go. There's our frequency of there's our input. It goes from 5 to -5. And then we're going to put this frequency is 100, and that, let's go back and look. Where's 100? 100 is right here. So that's right in the pass band. I should have a gain of 10. And that's exactly what we see, right? So we have the magnitude will be going from 50 and down to -50. You can calculate the frequency of this if you want. You'll find out that it is 100 radians per second. And the gain, again, is 10. So the magnitude goes from 50 to -50 since the input was 5 to -5. The other thing I want you to notice is that the input and the output are out of phase, and that corresponds to that minus sign in our gain equation. So what happens, you could do this by looking at it and knowing what the input was, 5 times the cosine of 100t, and you can figure out what the output is. So I just let MATLAB do that for me. Now we want to look at a frequency that's not in the pass band, and I think the one I chose was 0.1, which is right about here. Okay, so we can see that, sure enough, it's pretty attenuated. So it maybe doesn't look like a lot, but it's around 10 to the -1 times, so that's significantly attenuated. And when we look at the plot, okay, we have our input is still blue. Okay, it's still going from 5 to -5, but the output is now going from about 0.5 to -0.5. And the frequency is 0.1 radians per second. You can check that out yourself. Okay, so that's what happens if we put in a frequency below the pass band. We could do the same thing with a frequency higher than the pass band, and I think I put in 10 to the 10th. Okay, so if you look, our input, it's not a great looking input. Okay, it goes from -5 to 5. Okay, and the output is significantly attenuated, right? It's very, very small. But if you look, the frequency will be roughly 10 to the 10th. Okay, so let's go back and see what's going on in our graph. At 10 to the 10th, that's way over here. Presumably it comes down similarly. Okay? And again, in all these cases, the output and the input are out of phase, which corresponds to that minus sign. So there's a few practical notes we need to consider. So all the circuits we looked at really had a gain of minus ZF over Z1. Okay, so when RF goes to infinity, we would call that an integrator. And what that means is that you would just not put a resistor in there. So you would set it as an open. And the problem with that is if you had any stray voltage on the capacitor, it would integrate as a constant and create a big error. So even though the theory is good, in practice you don't want to do that. Also in a differentiator, that is when R1 is equal to 0 in the high pass filter, that's when you have a differentiator. And this again has a problems. You have a step change in the voltage. You end up derivatives are bad. So usually differentiators have a lot of error as well. So we don't usually build them in that exact way. So in all these actual implementations, you as the engineer must design the circuit to work under a lot of conditions, a wide range of temperatures, to be as cheap as possible, to work the same even with tolerances in resistors. And so optimizing the circuit for all these conditions is not easy. Fortunately, there are some standard designs you can use that will give you pretty good results.